Okay, welcome back to microeconomics. So let's talk about the first item of this week lecture, elasticity of substitution. What is that? So you heard about it last week when we talked about the production function, the constant elasticity of substitution production function, or the CES. And now what does it actually mean? We're gonna see. So the definition of elasticity of substitution, denoted usually as the sigma, is the proportionate change of the ratio between K and L over the proportionate change of the marginal rate of technical substitution of L for K when we move from one point to another point on the same isoquant. Now, and this, for very small change, we know about it already, can be approximated by the derivative of here the ratio of the input with respect to the marginal rate of substitution times the RTS over the input ratio itself. So this part is very standard definition of elasticity. We learn about it now. But then this is new. So it's actually equivalent to the derivative of the natural log of the ratio, the input ratio, with respect to the RTS. From now on, I will only talk about the RTS, like for simplification, and you also understand it like we're talking about the RTS of labor for capital here, like we always talk about since last week now. And one thing to notice is this elasticity larger than 0. Okay, so this part you know already now. These two things, why it's usually larger than 0 and why we can take the derivative of the natural log. I show you now. Let's start first with this. Let's jump a little bit ahead. So you might have seen already, if not then you will see it when you encounter some econometric classes. For example, the summer term with me, if you tend to take, sometimes you see that people will take the regression of an equation this form, which is the natural log of y equals some constancy plus b, the coefficient, times the natural log of x plus some error term. Just error term. Don't have to vocabulary now. And then the estimated b coefficient can be interpreted as the elasticity of y with respect to WRT with respect to x. How can we do that? It has a reason behind. So actually b is the slope of this equation. It can be treated as, now if you treat the natural log, the ln x, as a variable, not x but ln x, and you take the derivative of the ln y with respect to ln x. It is b, right? So here, if you treated these two as variable itself, not as the log of a variable, it has a reason behind why we could do that. Example, let's take our production function, the Cobb-Douglas, equal a to times k to the power alpha times L to the power beta. This is what we've seen last week, right? So now let's first take the elasticity, calculate the elasticity of Q output with respect to labor. Now, by definition, that would be the derivative, the partial derivative of output with respect to L, labor, times L over Q, right? Do it quickly here. So the partial derivative of Q with respect to L is A times K alpha, write it again, constant, L to the power beta. So exponential first times L to the power beta minus 1, right? This is the derivative. Times L again, divided by Q. So Q, let's plug Q again here, A, K to the power alpha times L to the power beta. Now let's simplify it. We have A over here and A in the denominator, so it's gone. You have beta here but nothing in the denominator, so it should be beta times K to the power of alpha, here K to the power of alpha, simplifies, gone. L to the power of beta minus 1 times L means to the power of 1. So beta minus 1 plus 1 is beta, and in the denominator you have beta, so it's gone actually. So the elasticity of output with respect to L is beta. Keep that in mind. So now if we take the natural log of this production function, we take the natural log of both sides, denoted as equation 1. We have the natural log of Q equal the natural log of A times K to the power of alpha times L to the power of beta, right? And by definition, the natural log of a product of many factors will equal the sum of the natural log of each of these factors, which is ln A plus ln K to the power of alpha plus ln L to the power of beta, right? Okay. And then you can also rewrite it in the way that I wanted to have two different L. For ln, just this simply. ln A, rewrite. So ln K to the power of alpha, you can write it equivalent to alpha times ln K plus similarly beta times ln L, right? Okay, very good. Again, if you applied this, treating the L and Q as some variables and L and K and L as variables, you could have the L and Q taking the derivative of both sides with respect to L and L equals. So here there's no L and L inside, constant, so it's 0, plus similarly here 0. There's no L, right? No L and L. And here you have L and L. So the derivative of a constant time a function, which is that constant time the derivative of function itself, right? With respect to L and L itself. And this is beta, right? And the beta here is exactly the same as the elasticity you calculated. However, I guess you might still be confused with that. How could we do that? Like, how could it be so easy that you treat the ln L as a variable, right? Still, I show you that if you don't take the derivative of this ln Q with respect to ln L, but rather the L itself, the labor itself. It could yield the same thing. So let's do it here. So now if you take the derivative of both sides of equation 1 with respect to L, not ln L but L. Now, then you would have on the other side the derivative of d ln A with respect to L plus the derivative of, again, constant alpha can go first, d ln K with respect to L itself plus beta, and then the derivative of ln L with respect to, okay. Now, on the left hand side, you can apply the chain rule. Right? Because ln Q is a function of L, but first of all, it's a function of Q. So we take the derivative of d ln Q with respect to Q times the derivative of Q with respect to L. Now, and that is for the left hand side. For the right hand side, it's right here. Again, because A is constant, so it's 0. Similarly, there's no ln K, so it's 0. And beta. Remember, one rule of taking derivative of the natural log of a variable with respect to that variable is 1 over L. Right? So now you have this. I put it over here. Hopefully we still have enough space. Then here you have the derivative of ln Q with respect to Q, the same rule here. So equivalent, we have 1 over Q times the derivative of Q with respect to L equal beta over L. Now if you I missed one D over here, DL now. This L is a little bit ugly, but that's fine. Then now if we multiply both sides by L, what happened? We will have L over Q times dQ over dL equal beta. And this is exactly the elasticity of Q with respect to L, right? By definition. So for that reason, back to here, the elasticity of substitution is the derivative of the natural log of the ratio, the input ratio, with respect to the natural log of the marginal rate of substitution of L for K itself. And actually this is, if we use our conventional notation of elasticity, you can write it as the elasticity of K over L, the ratio, with respect to RTS, L for K, right? So that's the first part. Okay, I show you why the sigma is larger than 0. Now imagine we are from this point, point A, now, and the slope of the isoquant at this point is RTS A. We're talking about RTS L for K, right? And here you have another point B, which the slope is the minus of the RTS B, right? And from what happens when you move from point A to point B, think about it. Here is KA, LA, the combination of input, and here is KB and LB, right? From RA to B, KA larger than KB, right? So K decrease. On the other hand, we have LA smaller than LB. So L increase, right? And how about the RTS? Let's do it best with an example of the CD production function again. So again, K over L will be decreasing, right? Because the numerator decreases, the denominator increases. So the ratio will decreases from A to B. Okay, keep that in mind. So we have again A, K alpha, L beta. Do it really quickly. RTS L for K equals MPL over MPK equals, I take the derivative directly here now, A times beta times K to the power alpha times L to the power minus, beta minus 1. We just recently did. And in the denominator we have A times alpha times K to the power alpha minus 1 times L to the power beta. Simplify. Here we simplify everything, and here you also can simplify everything. So at the end you would have beta over alpha times K over L. This is the marginal rate of technical substitution of K for L with the CD. So now, when you move from A to B, we said about that K over L will decreases, and RTS will also decreases. Because here you exactly have K over L, right? But this can also be generalized for many production functions. So now the RTS, or the elasticity of substitution, the sigma, can tell us about the curvature of the isoquant. So let's say you have this case where the curve's really curved. What happens here? Here, when you move from one point, let's say it's here, along the isoquant, you see that the slope or the RTS changes really rapidly, right? So that means RTS changes a lot per K over F changes, right? And because of that, the elasticity of substitution will be low because we have RTS in the denominator, right? And K over L on the numerator. On the other hand, if you have this kind of isoquant, let's go first with the very extreme case, the linear. What does the linear say? I mean, along this isoquant now, your K over L changes, but the slope of it or the RTS constant. So in this case, the sigma will be very high, right? And one less extreme case is very flat isoquant. It's like this, much flatter than here. Then in this case you have RTS change little per ratio change, and that means sigma will be high. So the key point to remember, the higher the RTS, the easier it is to substitute between the inputs. When it's so curved like this, the RTS will change rapidly when you move or when you change your input mix, and that implies a hard or difficult substitution among input. Now, there are two cases that RTS can also, or the sigma can also change when you scale up the production. So one case is like this. It started like low, at low level Q0. It's very curved, so hard to substitute. But the more you scale up, the flatter it gets. At the end it will be linear, maybe at some point. So that implies that there's one case when you scale up, it's easier for you to substitute between capital and labor. However, the other way around can also be true. When you scale up, the more you scale up, it's harder to substitute the input for one another. So the sigma, the elasticity of substitution, can change with production scale. Even though for the examples of production function that we talked about last week, the linear, the Cobb-Douglas, and the CS, is all elasticity, the constant elasticity of substitution. I show you. So I show you continued with the example of the Cobb-Douglas production function and see whether the elasticity of substitution is constant in this case now. So we have RTS L for K equals beta over alpha times K over L. We could rearrange it in a way that alpha over beta times RTS L for K equals K over L, right? Now let's take natural log of both sides. So you would have K over L equals the natural log of alpha over beta plus the natural log of the RTS, right? I skip the L for K there, but it's there now. Then you take the derivative of, with respect to the natural log of RTS, right? By definition, here this one is gone, plus the derivative of RTS with respect to itself. Sorry, the natural log of RTS, not RTS. So that equals 1. So in this case, the sigma is constant 1 as you move along the isoquant. Now, you can do it for the CES, linear fixed proportion. And you may find somewhere in the textbook where they show you that actually these function and the CD function is just a special case of the very general production function, the CEX. Now, check it out.